Good evening, everyone. Welcome back to the next session of DSA Cohort by Fluxus. So we were in the course of discussing tree data structure. So we'll continue with that into this session, and we will be discussing AVL trees and red black trees. So let's wait for others to join, and then we will start with this session. So guys, let's start with today's session. So so Kavya, I guess the team can answer your query in a better way because I am already concerned with the teaching part here. Okay, so the team will get back to you over this issue. So let's start with today's topic, and today's topic is AVL trees. As you have already, as we have already discussed, different types of trees, and that were generic trees, that where there is no limitation on the number of children, binary trees where there is a limitation that the number of children should be at most two, and then there were n-ary trees, that means the number of children are n. Then now in binary tree also we have some sub generalizations. And what was the specializations? What was that? The first one was a complete binary tree. And what was a complete binary tree? A complete binary tree is such a tree, complete or full binary tree is such a tree in which uh, all the trees, all the nodes have either zero children or two children. Now there was a concept of a balanced binary tree, and in a balanced binary tree, what was happening in a balanced binary tree? The height of the left subtree and the right subtree was differing by at most a value of 1. That means the balance factor was 1. And what was balance factor? Balance factor is nothing but height of the right subtree minus the height of the left subtree absolute value. Now, then we discussed something known as binary search tree, wherein I told you, wherein I explained that binary search tree is just a special case of a binary tree in which the binary search property sustains. And what was the binary search property? That at any given node, the left child will have a value lesser than the node value, and the right child of that node will have a value greater than the node value, and this will sustain for the entire tree. That means for any given node, the left subtree, elements of the left subtree will have values lower than the root node, and all the right subtree values will be greater than the value of the root node. This was balanced tree. Now what is an AVL tree? The first of all, AVL tree is you might be thinking the binary tree is named because of two elements and so on and so forth. Okay, good evening Antara. So what is an AVL tree? So AVL tree is not a meaning in itself. AVL tree stands for the name of their inventors. Okay, and what was the name of the inventor? The name of the inventor was Adelson, from where we get the A, then Welsky, from where we get the V, and Landis, from where we get the L. So AVL trees are named after its inventors. Now, what is an AVL tree? So AVL tree is just an addition over the binary trees, or we can say binary search tree is just an addition over the binary search tree. Or as I can say that it's just a solution to a problem that a binary search tree can get into. Now, what's the problem that a binary search tree can get into? Let me discuss this with an example. Suppose suppose I have a tree that looks something like, I have some say elements 64 and 24. Now what happens? I am and suppose I also have an element named 79. Now what happens here? I am tasked with constructing a binary search tree using these elements. So what will I do? I'll first insert the node with a value of 64. Now 24 will come into my scan. So what did I compare? I compare 64 with 24, and now 24 is lesser than 64. So adhering to the binary search property, what I'll do? I'll append 24 to the left child of the tree. Now, for similarly for 79, what I'll do? I'll append 79 to the uh, right child of the tree. Now, in this case, this is a binary tree. This is a full binary tree or complete binary tree. This is also a balanced binary tree. Why this is a balanced binary tree? Because what is the height of the left subtree? It's 1. What's the height of the right subtree? It's also 1. So balance factor. We already studied a concept named as balance factor. So what was balance factor? Balance factor was nothing, just the height of left subtree minus the height of right subtree. Okay, so balance factor for a um, binary search tree, balanced tree should always be in the range of 0 and 1. Can be at most 1. So in this case, the balance factor is 1. So it is a balanced binary tree. Now let's and it is also a binary search tree because it is a binary tree with the property of a property of binary search on it. So this is an example of binary search tree. Now let's suppose I get one more element here. What I get here is I get an element named 82 and then a 90. 82 and a 90. So what will happen? What will happen is it will get compared with 64. No, it's greater. It will be move on to the right child. Now that it compared to 79, 82 is greater than 79. It will get appended to the right child of 79. Similarly with 90. So in this case, what happened? In this case, what happened? By just appending 82 and 90, what happened is the tree is a binary tree now. The tree is a binary tree now. The tree is a binary search tree now. Is a binary search tree now. But what's happening here is this is not a balanced binary tree. Why it is not a balanced binary tree? Because here the height is 1 and in this side the height is 2. So sorry, I made a mistake here. Here the height is 0 and here the height is 2. So what will happen here is the absolute value will return a value of 2 and the balance factor is 2. So that's why this is not a balanced binary tree. So binary trees have this problem. What is the problem with binary search trees have this problem, and what is the binary search trees problem? Key with increasing number of elements, if we get on getting elements in either monotonically increasingly manner or monotonously decreasing manner. That means all the elements are either arranged in the ascending order as happened in this subarray or either in the ascending order. So what will happen is either the left subtrees left childs will get on appended. So my binary search tree will either look like this or only the right childs will get appended. So binary search tree will look like this. In both the cases, what will happen is the left child will be left length will be greater than the right length. So what will happen is the tree will lose its balanced nature. So a tree that was previously a balanced tree, a tree that was previously a complete binary tree, will now be reduced to just a binary tree with binary search property on it. Okay, to solve this particular problem, what AVL suggested is, what these people suggested is, कि we use a tree that will not just insert newer elements but also rebalance itself. It will maintain its balanced property with the addition of this new element too. So what are AVL trees? So in short, AVL trees are just an interesting addition to binary search trees. They are such binary search trees that are intelligent enough to do a thing known as self-balancing. What AVL trees does is AVL trees are just a binary search trees that are balanced, and with the addition of the new element or the deletion of any element, they rebalance themselves. They perform an algorithm known as self-balancing, by which the balanced nature of the tree is preserved. What I mean by this is, let me show this with an example. Suppose that I have a monotonically increasing array of elements from which I need to construct a binary search tree. Now suppose this is my elements. So what will happen? The tree that will get constructed for this is 10, 14 as the right child, then again 19 as the right child. This is a binary search tree. Why? Because all the left childs are null. But is this a balanced binary tree? No, because the left child length is nothing and the right child length is 2 here. Sorry, 1 here. So what will happen is this is not a balanced binary tree, a balanced binary search tree. So what will happen now? Suppose that we have constructed not a normal binary search tree, we have constructed a binary search tree that was an AVL tree. means this binary search tree can perform self balancing. So what will happen is, in this particular case, what will happen is, by default this tree, by default no, by its intelligence, this tree will get to know that I am not balanced at this particular stage. So if I make 14 as the root node, so what will happen? 10 will go here, 19 will go here, and now I'll be a binary search tree, but I'll also be a balanced binary tree. This particular tree is just a binary search tree. I have converted this to a balanced binary search tree. Okay, so if I'm doing this manually, then this is a manual operation. But if a tree is intelligent enough to do this thing on its own with the addition of 19, so what will happen is this tree will be called an AVL tree. And the intelligence that is applied here, it is not an sort of any intelligence, it is just a set of operations that we call as rotations, that we call rotations. So what are rotations? Rotations are a set of operations that are performed by AVL trees to regain their balanced form. So what are the rotations now? What are the set of different rotations? So we will just discuss this now. So there are 4 rotations that can that a AVL tree can perform to rebalance itself, to perform the thing that is known as self balancing. Okay, the first one is a left rotation. Second one is something known as a right rotation. Then left right rotation. Then a right left rotation. In simple terms, left rotation means rotate from the left direction. Right rotation means rotate from the right direction. Left right means rotate in 2 steps. First rotate to the left direction, then rotate to the right direction. What right left means is, first rotate to the right direction, then rotate back to the then rotate the left direction. So we'll now discuss what is left rotation, right rotation in details. So okay, so let me take one example here. By the way, this is known as LR, this is known as RL. Some textbooks also say this as RR rotation and this as LL rotation. In simpler terms, this is just a left rotation and a right rotation. My mistake. Left rotation is known as an RR rotation and right rotation is known as an LL rotation. Uh, in simpler terms, you can remember this as LL is for clockwise and this is for anti-clockwise. Uh, don't go into technical terms here. We'll first discuss, then you will not have to even remember what is a LL, what is RR, what is clockwise, anti-clockwise. So let me just take one example. Suppose that, take the example of my example that I took previously. Suppose I have a monotonically increasing element array, an array with monotonically increasing elements. So what will happen if I construct my basic binary search tree? What will happen? This will be my tree. This will be my tree. And what will happen is that the last term that changes the balance structure, because still here it is balanced. The height in the left side is 0, the height in the right side is 1. So till here it is balanced. Till here, with only 2 elements, the tree is balanced. the balance is disturbed when 13 is introduced. So you can just look for three logics here. Either the new element is inserted as the right child, as the right child of the right child. That is why the name RR rotation. From that only RR rotation. Okay. If the new element is inserted at the right child of the right child, then, and if the balance is disturbed in this case, what we do is we perform an anti-clockwise rotation, or you can also say that we perform a left rotation. Anti-clockwise direction is nothing but a left rotation. So what I'll do is I'll perform a left rotation in this case. So how will I perform a left rotation? I'll just do this thing. What I'll do is I'll just rotate this particular thing in anti-clockwise direction. This is what left rotation is. So what will happen if I rotate this? 10 will go down and 13 will be here. Now this is a balanced, this is a binary search tree because it is having the binary search property. It is fulfilling the binary search property, but also it is a balanced tree because 0 minus 0 is 0 only. The balance factor is 0. So this is what RR rotation is. That is, if the new element is inserted, if the new element that disturbs the balance of the binary search tree or the AVL tree, because we are discussing balancing binary search tree, is inserted as the right child of the right child. So what we do is we perform a anti-clockwise rotation. By anti-clockwise rotation or the left rotation, you can either say both, any of them. And by rotation, what we mean is we bend it down. We bend that edge down. We bend that edge down. And after that performance, what's happened is I get my balanced nature again. Anti-clockwise oblique left rotation. Any doubts still here? So this is how a binary search tree is balanced in case when the new element that is inserted in the right child disturbs the balanced nature. Now the second rotation is known as something known as left rotation or right rotation in simpler terms. Left rotation, and as I remember it, as a right rotation. Left right I mean how do I have to change the terms. This is how I remember it. And LL means the left of the left child. So what will happen is, suppose I have a monotonously decreasing array from which I have to construct the binary search tree. Suppose I have an element looking like this. So what will happen? The binary search tree will initially be looking like this: 12, 14 and then 12. Till here the binary search property is maintained and also the tree is balanced, because here the subtree's height is 1, here the subtree is null. So now what will happen if I insert the next element 10? By the insertion of this third element, what happens is that the tree remains a binary search tree, but its balance is affected. Okay, so what we'll do in this case is, so this, why is this disturbance happening? Because the new element is inserted at the left child of the left child. So if such a disturbance is happening, what will we do is we'll just perform a right rotation or a clockwise rotation. Right rotation or a clockwise rotation. Okay, so what we will do in this case is we'll perform this rotation. We'll bend the tree in the right direction or in the clockwise direction. So what will happen is the tree becomes this. Now the tree becomes this. This is a binary search tree and this is also a balanced binary search tree. Okay, and as this particular tree is self-balancing itself, so this is an AVL tree. AVL tree is nothing but a binary search tree that is capable enough to maintain its balanced nature. Okay, now to the next rotation that is performed on a binary search tree or AVL tree to get back its balanced nature is an LR rotation. What is an LR rotation? LR rotation is just a double rotation. What was a left rotation, right rotation? This was just single rotation. We are performing rotations in the singular in just one time. We were performing rotations one time. We were just bending one edges. LR rotation and RL rotations are nothing, just performing the rotations twice on two edges. Okay. See, when will this happen is, suppose I get an array like this. Suppose I have an array of elements looking like this: 12, then 10, and then 11. 12, 10, and 11. So how will the tree be constructed? The tree will be constructed something like this: 12, balance is maintained; 10, the balance is maintained, but 11 will be inserted as the right child. 11 will be inserted at the right child. Means the balance is disturbed by a node that is inserted as at the right child of the left child, at the right child of the left child, at the right child of the left child. So to rebalance this tree, we have to perform two rotations. Okay. So first one, what we will do is we'll try to convert we will try to convert this particular structure in a structure that looks something like this, because we already know to how to get balanced tree from this structure. So what we will do is we will just balance it in such a manner, such that the tree that is currently looking like this, left ka right child, will be converted into left ka left child. Okay. So perform this, what we will do, we first perform a rotation that looks something like this. We first perform a rotation that looks something like this. We rotate the positions of 10 and 11. We will rotate the positions of 10 and 11. So what is this rotation? This is just an RR rotation that we have discussed previously, or a left rotation, or a anti-clockwise rotation. Okay. So we first perform this. So what will happen is, after this rotation, 12 is there, as 11 needs to come at this position, so it will become coming here. But as now 10 is remaining, so what will happen is 10 will get appended, as 10 is less than 11, so it will get appended as the left child of 11. Now after this, what we are getting, we are getting back to my previous questions that we have already discussed, how to balance this particular structure. So what we were doing, we were performing a rebalancing in this manner. We were bending this particular uh, edge of the tree. So what is happening here is ki a LL rotation is happening, or a right rotation, or a clockwise rotation is happening. Okay. So what will the structure after this? The structure will be something like this. And we already know, if the structure looks something like this, the tree is now balanced. So LR rotation means when the balanced nature of the AVL tree or binary search tree is disturbed by a node that is inserted as the right child of the left child of the concerned node. So what we do is we perform two rotations, two subsequent rotations. First rotation is an anti-clockwise rotation, which converts this particular structure to a left ka left child structure, this structure to this structure. And after this, we already know how to convert this structure into a binary search tree, balanced binary search tree. That is by performing a LL rotation or a right rotation. Okay. In similar fashion, we perform a RL rotation. What is an RL rotation then? RL rotation is nothing, just a rotation in which the balance will be disturbed by the left child of the right child. So what is happening here is, suppose I have an array that looks that has elements in such a manner: 12, 14, and then 30. So how will the binary search tree will be constructed for this particular tree? It will be constructed something like this: 12, 14, 12 का right child, and then 14 का left child. And by this particular structure we can know that the tree is unbalanced. The tree is unbalanced because here the length is 2 and here the length is 0. So the balance factor is 0 in this case, sorry, 2 in this case. So that's why this tree is not balanced. So how will I balance this tree? So just like ll rotation, what I sorry, lr rotation, what I'll do is I'll try to first convert this structure which is looking like this to a structure that looks like this, because we already know how to do rotations to convert this into a binary search tree, balanced binary search tree. How we will perform this particular rotation: a anti-clockwise rotation or a left rotation in this case. So we know after this rotation the structure will look like this. So first task is to convert this structure into this structure, and we do this by performing we have to make this come here. So we'll perform a clockwise rotation here first. We'll first do a clockwise here, or you can say we first perform the right rotation here, or we can say that we perform an L rotation first. Okay, so what is happening after this? The structure becomes something like this: 12, 14, and sorry, 12, 13, and then 14 as the right child. So now we already know how to balance this particular structure. So what we will do is we will perform a anti-clockwise rotation, anti-clockwise, or a RR rotation, or a left rotation. And after this, how will my structure of the binary tree look like? It will look something like this: 12 as the left child of 13 and 14 as the right child of 13. This will be my structure, and this will be a balanced binary search tree. And the tree is performing all this on its own. That's why it is an AVL tree. So what is an AVL tree in short? AVL tree is just a self-balancing binary search tree, okay, that maintains the balanced structure of the binary search tree with every new insertion or every new deletion. So now suppose that I try to delete one of the nodes. So what will happen is I'll delete some of the nodes, and by deleting some of the nodes, what will happen? The balance property will get disturbed. So what will happen is it will perform either of these 4 rotations: LL, RR, RL, or LR rotation to rebalance the tree, and then insert that particular key in its right position, or after deletion it will rebalance itself to again look like a balanced binary search tree. Okay. So let's look at one example, okay, to solve our query here. Okay, let's suppose I have to construct a tree with these particular elements: H, I, J, B, A, E, C, F, D, G, K, L. I have to insert these elements, and suppose these are in their dictionary order. Means A is less than B, B is less than C, and in such a manner. Okay, in the dictionary order. So what we will do here? Okay, so let's just construct the binary search tree here. So what we will do is we'll first insert H in my binary search tree. So what will happen? H gets inserted, and what is its balance factor? It is 0, because there is no left tree or the right tree here, so right subtree here. Now I comes here. Now I comes after H. So what will happen? I is greater than H, so I will be inserted as the I will be inserted as the uh, right child. Again, what happens after just the insertion of this thing? After the insertion of this particular thing, what is happening? The balance factor gets updated. What is the balance factor of I now? The i's balance factor is now 0, but for h it is now how much? It is 1. No, it is -1. Why? Left minus right, we do know. The left child is 0, right child has a length of 1, so it is having a balance factor of -1, because 0 minus 1. We follow this funda: length of height of left tree minus height of right tree. Okay, now also the tree is balanced because 0 and 1 is allowed. Now let's we take into account the third element. Now the third element is j. J is also greater than I. So with the insertion of j, what is happening? Just as j gets inserted, the balance factors again changes. For j it becomes 0. For I it becomes -1, because 0 minus 1. For h becomes 0 in the left side and 2 in the right side. It becomes -2. And because of this -2, what are allowed numbers in balanced tree? It is 0, 1 and -1, if you take absolute values. So 0 and 1 are only allowed. So because of the insertion of this j, the balance factor of h becomes -2, and hence this tree loses its balanced nature. So in this particular case, what we have to do is, before inserting any other element, we'll have to first balance itself. So as balancing is disturbed, so what we will do is, first we will perform balancing. So how we will perform the balancing? We'll perform balancing in this particular manner. As we already know, the balancing is being disturbed by the right child, of the right child. So what kind of rotation we have to perform here? We have to perform a RR rotation. And what was the RR rotation? RR rotation was just a left rotation or an anti-clockwise rotation. What I have to do is, I just have to rotate this in this manner. So what will be the resultant tree here? The resultant tree will look something like this. Resultant tree will look like I in the middle. I think I drew the arrow at the wrong place. Sorry, my bad. I'll perform a left rotation. So H will go down and J will come here. This will be the structure, and this is a balanced structure. So after balancing, what happens is the structure gets changed. I becomes the root node, H becomes the left child, and J becomes the right child. And why it is balanced? It is balanced because this has a balance factor of 0, this also 0, this also 0. Now what we will do, we'll scan B now. So as B is there, okay, so where will B get inserted? B will get inserted because B is less than I, so left side. B is again less than H, again left side. So where it will be inserted? It will be inserted as the left child of H. Now again, let's check what the balance factors. For this it is 0, for this it is 0, for this it is 1 now, and for this is again 2 minus 1, so this is also 1. Again, balance nature is preserved. So what's the next element? Next element is A. So where will A go down? A is less than I, so left side. A is less than H, left side. A is less than B, again left side. So A will go down here. I, H, B, A, and then J. Now recompute the balance factors. Here it is 0. For this it is 0. For this it is 1. This it is 2. 1, 2. And for this it becomes how much? For here this is 3. Here this is 2. 1. 3 minus 2 is 3 minus 2. 3 minus 1 is 2. So now we can clearly see that the balance factor for two nodes, for H node and for I node, are 2 and 2, which disturbs the balanced nature of the tree, which disturbs the balanced nature of the tree. So again, what we will need to do, we'll need to perform balancing here. We'll perform a balancing here. Okay, I guess I have exhausted the place, so let me just okay, no problem. Just pick this up. Okay, so we were discussing just this thing. Okay, so now as the balanced nature gets disturbed out, so what we will do is we will again perform balancing here. So how will I perform balancing here? So let's look at the downward side. Let's reconstruct the tree. I, J, H, B, and A. For which insertion the balanced nature gets disturbed? For this particular insertion, and where has this been inserted? This has been inserted, and what are the first node whose balance has been balance factor has been disturbed? H. So where is A in relation to H? It is in relation to as the left child of the left child, left child of the left child. So what kind of rotation we have to perform here? We have to perform a LL rotation here. And what's a LL rotation? LL rotation is just a right rotation or the clockwise rotation. So what we do need to do here is we need to do a clockwise rotation here. And what is a clockwise rotation? Clockwise rotation is just this thing. Rotate this particular thing. So how will this get rotated? This will get rotated as B as the center, A here, and H here. A, B, H. Okay. So what will happen is this tree gets converted like this. B, A, H. As A gets down, so B will become the direct child of I and then J. So let's recompute the balance factors and see if we have solved the issue. Here this is 0, 0, 0. For this also it becomes 0 only. For this it becomes 1, and for in this side this is 2. So 2 minus 1 is 1. So the balanced nature is preserved. So after, where did I go? So after this particular operation, what happens is the balanced nature of the tree is preserved. Okay, so we will just place this particular structure after this operation. So after rebalancing, what happens is I becomes the node, root node, J becomes the right child, B becomes the left child, H becomes the right child of B, and A becomes the right child of H. So again, let's see what's the next element to be inserted. The next element to be inserted is E. So again, something will happen. The tree will, after the insertion of E, either we will compute the balance factors. We'll compute the balance factors. If for any case the balance factors changes from 0, -1 or 1 to 2, 3 or any other number, what we have to need to do, we'll have to look for the right rotation that we need to perform, and then we will perform that rotation, rebalance the tree, and then we will get our final balance tree. Okay. So Ravi is asking, balance factor can be 0, -1 or 1. Yes, Ravi, the balance factors can be in the range of 0 and 1 in the absolute values. That means that 0, -1 and 1 is allowed. Okay. So this particular structure is allowed. 2 in the right child or 1 in the left child, 1 in the left child and 2 in the right child, or both sides equal number of children. All these three structures are allowed. Other than these, any structure is not allowed. You can think it like this also. Okay. So any doubts still here? So this is the whole concept of an AVL tree. What is an AVL tree? AVL tree is just a tree, just a binary search tree which can rebalance itself, which can perform a self-balancing on it by the means of the four rotations. And what are the rotations? Rotations are nothing but LL rotation, RR rotation. LL means rotating in the right direction. RR means rotating in the left direction. LR rotating first, RR, then LL. And what is RL? RL means rotating first LL and then RR. And this LR, RL, LL, this all means where the, with the insertion or deletion of which node does my node becomes, that my tree becomes unbalanced. So whether it is a left ka right child or right ka left child or left ka left child or right ka right child. So this is our concern here. So now let's move on to the next topic in hand. By the way, this is a binary search tree only. So all the operations in an AVL tree will take log n time, and in the worst case, it can take a O of n time. Okay. So for the time complexities, if anybody is interested in time complexities, so sorry, my bad, because in binary search tree, what was happening in the worst case, binary trees, we can go up to O of n, but here, as at any given time the tree is balanced in nature, so all these search operations will take log n time. Insert operations will also take log n time, and delete operations will also take log n time. Okay, both in the best and the worst case. What I'm telling here, search, insert and delete all take O of log n complexity, and log n complexity, both in the best case and the average, average case and the worst case. Best case, so we are never interested in for an AVL tree, because at any given point of time my tree will always be a balanced binary search tree. Okay. So now let's move on to the next topic, that is a red black tree. By the way, any doubts still here, you all can post it in the comment box. If not, then we will move on to red black trees. I'll wait for 2 minutes for your comments, and then I'll move on to red black tree. I'll just do a brief introduction of red black trees. Okay, because I have discussed the ordered map STL, and you can get asked in by anybody that anybody can ask you what's the data structure that ordered maps are built on. Ordered maps are built on red black trees. Okay, so what is a red black tree? You must know about this. Okay, and why do we use a red black tree? Just because search, insert, and delete takes a log n time. So if search, insert, and delete takes a log n time, this should strike your mind that this is a binary search tree, which is a self-balancing tree. So you can also think as red black tree as special case of an AVL tree. Something add on over an AVL tree means this will be a self-balancing tree because all the operations are also taking log n time. They are never going on to they are never going on to O of n. That means that this is not a normal binary search tree. Okay, this is something else, and this is a self-balancing binary search tree. So what's the interesting parts of a red black tree that we will know? What's the addition over AVL trees that a red black tree possesses? Let's discuss that. Okay, so basically a red black tree is a tree that has some properties defined on it. Let me just check the no, nobody has posted any comments. Okay, so what's a red black tree now? The red black tree is again a self-balancing tree, is a self-balancing tree, or we can say an AVL tree, with just one difference, that apart from the node, every node of this tree, apart from just containing the data and the left child and right child pointers, this also contains an extra bit. Extra bit means extra information. Extra information. And what's that extra information? That extra information is of the color. Is of the color. That is, either this color can be a red or a black. That means either either the nodes can store the data. Nodes are storing data in this case also. Node, the tree is self-balancing itself, but the node has an extra bit, that is what's the color of this particular tree, what the color of this particular node here. Okay, so okay, so I'm again waiting for your doubts. If not, then I'll just move on. Now you will be getting you will can ask me, is binary search tree can solve my questions? Okay, there was a problem with binary search tree that it does not remain balanced by itself, so we have introduced AVL trees. So a binary search tree which can rebalance itself, self-balance itself with the given time. So what's the need of a red black tree? What's the need to increase one bit in the node to store the color? What's its applications? So this red black tree finds enormous number of applications in the field of computer science. Tree in itself has enormous number of applications, humongous number of applications, and red black tree is one of those trees whose applications are enormous. Okay, and what are those? Number one, if anybody of you are interested in machine learning, then you must have come across this algorithm, k-means algorithm, that is used for clustering of data. So k-means algorithm inherently, if is applied using a red black tree, we can reduce the complexity of a k-means algorithm. I am coming from machine learning background, so I can tell you this. The many people ignore the fact that DSA is important when you are studying machine learning or any such stuff, because you can directly import packages. But in real life scenarios, there are cases. What's DSA? Why is DSA important? To reduce the time. If you are working as a backend developer, what you will do? You are interested in not just the API calls. You are also interested in reducing the time of the API calls. Okay, to give a flawless experience, seamless experience to the customer, to the client. In such a manner, also in machine learning, also the training times are very large. So we try to reduce them by any means. Some are developing GPU based algorithms to run the algorithms on GPU. So for k-means algorithm, Red black tree approach is one such approach that reduces the time complexity of the k-means algorithm. Second one is, all of you might have studied about MySQL. It's a structured query language. It's a query language basically. Okay, so MySQL also uses red black tree for its search operations, insert operations, delete operations. Whenever you do insert table, create a table, delete a table, drop table, sorry, delete a data, drop table, append a table, any such queries when you write. So at the behind, the developers that have coded the SQL algorithm, they have used red black trees. Again, for the fact that it has the login complexity for every operation, search, delete, and insert. That is why, so you can see MySQL or SQL in general is just the backend of many databases. Many databases use MySQL. I know most of the large companies like Postman, the whole servers, whole databases are based on MySQL systems. So they use MySQL. MySQL uses red black trees to implement itself. K-means algorithm can be optimized using red black trees. So you can just think of it कि red black tree is the ultimate thing we need to study in the trees. All the things that we have studied were just the basics to reach till red black tree. Okay, again, if you're using a CPU and your processes are getting scheduled on your CPU, while you will study in operating system course, that there is the term known as CPU scheduling algorithms, where we study the different algorithms that are used to schedule processes on a CPU. So if anybody uses Linux operating systems, okay, like I use Linux operating system. So Linux operating system uses there is a scheduler named as completely fair scheduler, which uses red black trees in its implementation to schedule processes on its CPU scheduling. Okay, MySQL uses for its indexes for the tables. Okay, and in C++ we have already seen the map, the ordered map that we saw as STL in C++ uses red black tree for its implementation. In Java, there is something known as a tree map. Tree map. Just for C++, there is an ordered map. In Java, there is tree map. Both use red black trees for their implementation. So you can just think of it, ki how much important this red black tree is in the field of computer science. Now let's move on to the properties on which a red black tree is composed, is constructed on. Okay, so let's see what are the properties that we need to know, or we need to see what differentiates a normal uh, AVL tree from a red black tree. Oh, sorry, a red black tree from a normal AVL tree. Okay, so let's discuss the properties now. So the properties is, first, so the number one property is the nodes are always colored. Every node of the tree is either red in color or black in color. Okay, now the first thing first, the root is always black in color. The tree starts with a black node. The tree starts with a black node. The root node is a black node. Now all the nulls, all the nulls, any null pointer is there, that is considered a black node. That is considered a black. That means that at the leaf, at the leaf node, okay, at the leaf node, the leaf node has null as the next pointer. So every leaf node must be a black color. Then the third thing is red and black should be alternate nodes. Red, if the root is black, the two childs must be red. Then again the children of those red nodes will be black. will be black. Then the children of those will be a red. Means we will never encounter black, and we will never encounter red. Red and black will always be consecutive to each other. There will be no two nodes that are directly connected to each other and are both red or both are black. Okay. Then, as it comes from the third property only, that if there is any black node, then for this black node, all its children are red in color. For any black parent, the children are red. Okay, so these four properties are there in a what we can say. One more property is there. I just it skipped my mind. This is known as a black height rule. Black height. In a normal tree, we have a concept of height. In a red black tree, we have a concept of a black height. What's the black height? The black height is the height of a tree. Black height is the height of a tree, or we can just say the length of the path from the given node from which we are considering it, and we are counting all the black nodes in that path. We will eliminate any red nodes if there are any. We'll just count all the black nodes that are present in a particular route, neglecting the the last nodes, that is the children node, leaf nodes. So this particular length is known as a black height. So the general definition can be the length, the downward length of the downward path is the number of black nodes in the downward path from a vertex V, or the node to to the leaf nodes. The distance, the length, downward path, the number of real black nodes. What are real black nodes? Real black nodes are any those nodes that have children, that do not point to null. Okay, so at a given path, downward path, from a node, say node 1 or node n, to the downward path to the leaf node, we just count the number of black nodes, real black nodes. That means the black nodes that have children. And that particular length, that particular count is known as the black height of a red black tree. Okay, and this particular thing can never be eliminated. Now, if suppose all the conditions are holding for a tree, but only the first condition is not holding, that means everything is holding, but just the root is not black, the root is red in color, then thus that kind of a tree is known as an ARB tree, almost red black tree, almost red black tree. So you can just also remember this. If any node starts from a red node and follow and has all the properties of a red black tree, then such a particular tree is known as an ARB tree, that is almost red black tree. Okay, in case of any doubts, you can post it in the comment box. We'll not be discussing the insertion or deletion on the red black tree. Okay, because as of now, so this is all the theory that you will ever need in tree data structures. And one more thing. The black height of all the nodes should be same. Means suppose suppose starting from the root node, there are four different. There can't be four different, as this is a binary search tree, so there will only be two paths. Okay, so let's suppose starting from the root node, there are two paths, and these two paths are subdivided. They get branched out in the later part. So any path that reaches the leaf nodes will have the same black height. Will have the same black height. This is also a rule of the red black tree. So there's some rule. The root is black in color. The root is always black in color. All the null nodes or the leaf nodes are considered to be black. There cannot be any two nodes that are of the same color, which have the same lineage or same parent child. The parent child cannot have the same color. They cannot both be red or both be black. Then every black node has a red child. Every black node has a red child. And there is something known as a black height rule. What is a black height rule? That is the number of black nodes in a particular path, neglecting the leaf nodes. Okay, so what's the black height rule? Black height rule says that starting from the root, whatever paths are there to reach the leaf nodes, in any given path, any path from a node, including the root node, to all its descendants, that is, till the leaf nodes are encountered, all the paths will have the same number of black nodes. Okay, these are the properties that are on which red black trees are based on. Okay, so with this we end the theoretical part of, we the tree traversals and all the things are left, but I have kept them for the coding part. When we will be discussing the implementation details of trees, then we will get into the tree traversals and all those things. Okay, for the theory part, the tree traversals are three in nature, that is in order, post order, and pre-order traversals, but those we will discuss tomorrow when we are discussing the implementation coding of the trees. Okay, so with this we end the theory of AVL trees and red black trees. That was today's agenda, and from tomorrow we will start with implementation of trees, then move on to tree traversals, then we'll solve some important questions on tree data structure. Okay, so with this I end the session here. Okay, have a good day ahead. In case of any doubts, you can post it in the comment box. I'm waiting. I'll wait for 3 minutes for any doubts, and then I'll end this session. The coding part will gets get started tomorrow. From tomorrow, next two sessions or next three sessions will be solely dedicated to coding part. We'll be coding the trees and different questions on it. I thought of not starting it today because these two topics were an important topic for theoretical purposes and also for coding bits of the coding part. So as hashing is already been discussed, and with the completion of red, black, and AVL trees, we can now move on to solving some really good questions on trees. So we'll move on to coding tomorrow. The attendance link will be shared with you shortly. Um, this will be sorted out by the team. Okay, the team will get to you all. Don't worry about this. Yes, Ravi, this is only I'm saying the team will get to you in a short while. Today's attendance is shared, I guess. Yes, today's attendance is already being shared. You all can mark your attendance there. And for yesterday's attendance, the team will get to you. Don't worry. For yesterday's attendance, the team will get to you. Don't worry about that. Okay. So, guys, as you all do not have any red, black tree or AVL tree related doubts, so I am going to end this session here. Uh, Great day ahead. Great learning sessions for you all. Good night.